Welcome to Webinar Wednesdays with Cadence PCB. My name is Jim Fry, and I'm the Product Marketing Manager for Cadence Allegro PCB, a family of EDA tools. This series of webinars highlights the latest in Cadence PCB 17.2 technology that can help you and your team improve your design while improving your time to market. Our guest expert today is Ed Atchison. Ed is a principal product engineer for the Allegro PCB products at Cadence, focusing on DFM, ECAD and MCAD, as well as the IPC 2581 consortium. Ed joined Cadence in 1990 and has played several roles, including software developer, consulting, and process services engineer. Prior to Cadence, Ed was one of the first ECAD users at Wang. Outside of work, Ed is an avid and sometimes rabid golfer. So to thrive in this competitive environment, you need the best tools for the job and you need to know how to use them. Here at the Cadence PCB team, we share your desire to improve your productivity while increasing your design quality. Because you are so busy, you may not have had a chance to stay updated on our progress, so we build this episode to quickly highlight key strengths of both Allegro and OrCAD for the complex world of flex and rigid flex. After watching this webinar and others in this series, you will know how and why Cadence PCB tools will help you keep your competitive edge. Although you may think Cadence is just PCB, it is clear that we have a wide offering, a full stack from system to board to package to chip. By bringing modeling and analysis further into the process and linking these models to constraint-driven PCB and system design, our tools are a vital part of many different companies' design workflow. We are engaged with many industry groups and key ecosystem players to connect our tools with others for the best integration possible. So what are our differentiators that will help your team keep a competitive edge? First off, you should leverage our constraint management system. The more design context you can give our tool in the form of constraints, the better, and the tool performs better that way. Correct by design. Get those known good circuits and PCB layouts into libraries as reusable modules. And you can improve your high-speed performance with our great backdrill annotation tools. And finally, make design enjoyable using our intelligent editing, dynamic shapes, application modes, and advanced contour routing. And finally, bring more materials into your design for assembly checks with specific support for flex and rigid flex. Okay, now let's get to it. Introducing Ed Atchison. On with the show.
Thank you, Jim. Hello, everyone. Thank you again for taking time out of your busy day and your busy schedules to attend this webinar series. So today we'll be talking about serious tools for advanced rigid flex and what has Allegro done for you lately. So we take a look at rigid flex and the growth of this industry. And over the past 10 years, it's grown from $1 billion industry to a $12.5 billion industry. And what's responsible for that growth? Well, we look at the technology-driven challenges that are faced today. We have unique contours such as dashboards and automobiles, lightweight and tough environmental conditions that require these rigid flex type designs. We look at the compact and lightweight devices, handhelds, wristwatches, things that are applied to clothing. All these require these types of materials that make it light and flexible for circuit design. Also, medical devices require a lot of rigid flex where they have to fold components together in a circuit to fit into a small housing such as a hearing aid. And in driving those types of technologies, unique materials are used in the rigid flex environment as well. We see different types of polyamides, their thicknesses vary, types of platings, protective materials, different surface finishes, golds, tin, silver, and we see various thicknesses across these designs too, where you may have a rigid section that could be 8 layers that goes to a 2-layer flex and into a 4-layer rigid. And then there's bending criteria that has to be defined. If I fold this particular design in a certain way, what is the criteria for that bend, and what type of interferences will I run into with that bending? Understanding placement in rigid flex is very critical too, and some of those details. If I'm placing a component on a 6-layer portion of my rigid flex design and place others on a 4-layer section of my rigid flex design, does my CAD system understand those different plane layers that the components are resting on, and how do I transfer that information forward to my manufacturing? And another challenge in the rigid flex space is passing on the design intent from the design system to the manufacturing floor, and a lot of that requires a great deal of documentation and what things can go on to improve and make that description of my design intent much more clear to the fabricator, and what can be automated in that. So in Allegro PCB Editor 17.2, we focused a lot on rigid flex features. And some of the things that we've introduced first start with 2 new subclasses for rigid flex design. A specific rigid flex subclass, or class, that has a series of subclasses that were pretty much taken from our customers who have used and designed rigid flex layers before, and looked at the common layers that were used to define the rigid flex definitions. And so we've seeded the rigid flex class with those subclasses related to those. Surface finishes is the second class that was introduced that deals with the different coatings and plating materials such as gold and tin. Specific subclasses for masks that identify those layer types for fabrication. One of the most critical parts about rigid flex design is the ability to identify the different stack-ups across the design. As we know, in a real rigid flex design, the layer thicknesses and the materials will vary from one region to the next, or zones as you would call them. So that requires multiple stack-up definitions. If you're doing any type of inlay structure where you would have a RF design that you would like to inlay into a standard fiberglass board, cross-section details regarding those different stack-up types also needs to be defined in the Allegro editor. And the new stack-up or cross-section editor enables the ability to define those different masks, the different stack-ups for the different regions of the design. Part of that, the ability to add the multiple stack-ups, is now the ability to add mask layers outside of the outermost copper layers. So layers such as solder mask, paste mask, even silkscreen can be defined as a outer layer on the stack-up. To help you, the user, quickly define subclasses for mask layers or even some internal layers, we created a new mask site file where a library of materials and common stack-up names can be defined, and the user, when builds the stack-up, can quickly reference it and provide the proper layer stack-up information. So the mask site file, as you see here, defines a function. Now the function is an attribute driven by IPC 2581 that helps the manufacturer understand what that particular layer is designated for. Next is a name that sets the common subclass that could be used from design to design, as well as the class that that subclass is listed in, and then the default material for that particular subclass layer. This site mask file is located in the same location as a material.dat file through the material path environment setting. So when I add layers in my cross-section editor, the user interface that appears shows me a list of site-defined mask layers or design-defined mask layers. So if I create my own subclasses, I can get a listing of those as well. The difference between the two, if I have a design subclass, I would have to go through this user interface to define the particular subclass layer I want to use, the layer function for that, and the layer material. If I use the mask site file and select from that entry in this user interface, the subclass name I select, the layer function and layer material are already predefined, and there's no need for me to go in and specifically assign those. I can use what the default is as defined through the mask site file. So let's take a quick look at how this works. So here we see I have the new stack up editor, and in the cross section I have defined a primary, which is the root definition of my design. I have a 4-layer rigid stack up, a 2-layer flex stack up, and on the right hand side I can see the graphical representation of those subclasses. What I'd like to do is add a stiffener and create another subclass for a flex with a stiffener on it. So to do that, let's take a quick look at the site file and see if I have that material listed. So I do see a stiffener that is made of stainless steel, and it will appear on the rigid flex class. In my cross-section editor, I select Add Layers. The user interface displays. I select from the top listing my stiffener. Notice that the dielectric base is the function that's already assigned, and stainless steel material. And I can see a summary of that also at the bottom center of the form. It tells me what will be added. Select the Add button, and now this layer is populated into my cross-section. Once in this cross-section editor, I add the thickness of this material. And now I can go ahead and add a new stack up. I select the Add Stack Up, enter a stack up name, be flex with a stiffener. And to make life easy for me, I'm going to select the Flex 2 layer and copy the parameters from that stack up into the new stack up. And we can see the new stack up added. And on the right hand side I can see the graphics have been updated to show that stack up as well. So for this stack up I want to have the epoxy to adhere the stiffener, and unselect the stiffener from the other layer, the other stack up definitions that do not require it. And my stack up graphics are updated. That's how easy it is to add a new stack up definition. The next critical part of defining rigid flex is identifying where these various stack ups occur in my design. By doing so, we created a rigid flex zone capability. The zone is used to map an area of the design to a particular stack up. So the zone boundary itself is a shape that defines the external boundaries, and then it's tied into the stack up, and if need be I can add a constraint area or a constraint definition by creating a constraint area as part of that stack up zone, as well as define a room. So if I want to specify certain components to place in that room, I can do so. Zones also not only provide just the stack up information, but they're also critical when it comes to understanding the outermost layers for those different stack up regions or the stack up zones. These zones provide boundaries to prevent routing traces into space where a particular layer may not exist. It understands the outermost layer when I do my component placement. There are two basic tools for zone creation, and that is the create zone and manage zone. One I use to create the actual zones, and if I need to make changes later I can go back and manage those zones. So let's take a look at how these zones are created. So here I have a rigid flex design. I'm going to create a new zone where that stiffener layer that I created, I'm going to add that to a particular part of this design. So I begin the zone editor, enter a name for the stack up zone, select the stack up definition that's in the cross section editor and assign it to that zone. And now I defined the region where I want to place the zone. I can use a simple rectangle as I'm demonstrating here, or I can use a complex shape figure. The zone understands any adjacent zone, and it also understands the design outline and will trim that zone to those specific geometries. Now I'm going to add another flex zone without the stiffener. Again, I enter a new name, select the stack up for that zone, define the boundary, and once again the zone is added. Again, it is trimmed to the other zone outlines as well as the design outline. Now I'd like to make some changes to the zones that I've created. One of the steps that I neglected to do was to go ahead and add a constraint region. As we look at the form here, we can see the name of each of the zones, the stack up that's assigned to it, as well as the start and end layers of these stack up zones. I've now added the constraint region definition to the flex with stiffener as well as the flex zone 2. And as a reminder to the next person who may pick up the design, I will add a note that will be associated with the stiffener stack up so that the next user will understand why that stiffener was put in place. So this note is now attached to that stack up zone, and any time that I view that particular single stack up zone, I can see that note. Another critical piece for defining a rigid flex design is the ability to define a bend in that design. Bends have particular characteristics to them, knowing the direction or side where the bend will occur. We need to know a radius, the angle of a bend, the center location of the bend. This information can be exchanged through IDX, or it can be manually created within Allegro. The bend area is a composition of a bend line, a bend area itself, and the inclusion as options of via keepouts and package keepouts related to the bend area. When I define the bend parameters, these parameters are attached to the bend line and maintained through the bend line. Whether I maintain it within the Allegro design or if I pass that information off to a mechanical tool system, those parameters are passed along as well, specifically through IDX. Let's take a look at how bend areas are created. So I launch the bend editor, bend create. Each bend requires its own individual name. I next define the location of the bend line. I can either do it manually or I can enter the XY coordinates in the form. Specify the direction of the bend, whether I'm going to bend it upwards from top or downward from the bottom. The radius of the bend. And then the bend angle. And bend order can be defined to help in the order sequence of particular bends to prevent interference during the actual assembly process. The optional via keepout and package keepout definitions, they can be selected or unselected, and an oversized value may be defined for each of these objects. These keepout areas are based on the bend area calculated by the bend information. And hitting create, we can see now the bend area, the bend line, as well as the via keep-out and package keep-out definitions. Looking at the bend line itself, we can see the parameters for the bend area as we have defined them. If a change is required, I go into the bend editor. I select the particular bend name and make the change. In this particular case, I'm going to change the radius of the bend. Once I apply that, I can see how the bend area is updated along with the geometries associated to it. As mentioned earlier, one of the important aspects of the stack-up zones is for the tool to be zone aware, understanding how placement works, how routing works with these particular zones. In placement, we typically place components on the outermost layers with the exclusion of embedded components, and the placement of those components are supported in add, move, and mirror, just like it would on any rigid design, except it understands now the different outer layers of the particular stack-up zones. The placement is based on the origin of the symbol, so wherever the origin passes, whichever zone it's in, recognizes what layer that component should be placed in. And routing, of course, will not allow any errant connection to a layer that basically is floating in space. So let's take a look at how this performs. I have here a symbol that it was placed on the outside of the design, like a lot of us do before we do our placement, place them around the design, and it was placed on the top. It's highlighted by the red component leads. And now I'm placing it onto a 4-layer of my 6-layer stack up. And we see the leads are now pushed down to the top of that 4-layer package. Here we have side by side a 6-layer to a 2-layer stack up, and as I move the component across the zones, we can see the component lead change color, indicating the different top subclass of each of those zones. As I move this across again, I'll now do some other component manipulation, such as mirror it to the top of the flex, and I can see it's gone to that particular top layer. Move it back to my 6th layer, and I can see the lead color change for that, indicating that this component is truly being pushed to the particular stack of zone regions. Not specific to rigid flex design, but making etch editing much easier, especially when using curved traces. We've improved contour routing and crosshatch shape, making contour routing, crosshatch shape additions much more easier for the user. So I'll give a quick demonstration of that while I'll show some contour routing. I first begin by adding a power trace coming off of one portion of my flex design, and now I'm going to force that trace to hug the route keep-in area and follow the contour of that. And I also added a little bit of space away from the edge. As you can see, as I move my cursor around the design, the trace just follows along that nice smooth curve around my flex. I can also do this with a group of nets. In this case, I'm going to have them follow the power net, so I'll select connect line. I'll change my gap to 15 mils and space that a little bit away from the power conductor. And again, as I move my cursor across the design, we can see how it follows the contour of that conductor. As mentioned earlier, we spoke about trying to create a connection from a top layer on one particular stack up to the top layer of another and preventing that error from happening. I'll demonstrate that here. I'm trying to make this connection, and it's telling me that I'm not on a legal subclass when I cross that boundary of the zone. So I back it off, add my via down to the appropriate layer, and complete my connection. Push and shove routing also supports the contour process. I start adding my connection that I errantly missed, and now I'm going to tell it to follow the contour of the trace to the right and have it push the trace to the left out of my way. And as I move up, we can see again it's following the contour of the selected line around the bend. And now I can complete my connection. Adding crosshatch shape areas for ground is much easier. I set up my crosshatch parameters. Go into shape, add a net to the particular shape. In this case, it will be ground. Change my fill type to dynamic crosshatch. Again, the crosshatch was predefined. Now I select the boundary where I'd like the shape to be added. And understanding the route keep-in and geometries associated with it, quite easily, just with 2 picks, created a nice crosshatch shape. Another important aspect of rigid flex design is with so many different types of mask layers, cover lays, and other materials, many subclasses are used to represent these objects. And it can be beneficial to have some type of a check to make sure that all my gold is exposed in my cover lay, or I may have some requirements to keep bends away from stiffeners to prevent stiffeners from peeling. A set of rules would really be nice to have to prevent errors from occurring in that space. Allegro 17.2 introduced interlayer checks where I can now check those particular mask layers against each other. I define the 2 subclasses that I would like to create a rule for, define a rule, and the 3 basic rule types are gap, an inside check, which says if I have for instance, a gold pad inside my cover lay, I want to make sure that it's contained within that and does not cross over the boundary. And overlap, in particular cases where I want certain layers to overlap each other for a specific distance. These rules are defined in the constraint manager, which you know and love today. So let's take a look at a couple examples of interlayer checks. In this particular case, we have a stiffener that we've added to the design, and I want to ensure that the stiffener has a particular gap away from a bend. So in the constraint manager into layer check spacing, I filter for the stiffener as well as the bend area, select those 2 intersecting subclasses, define a gap rule. The value for that gap space in this case is 15 mils. I enable this check, and now I add my own DRC label, which is the right-hand character on the DRC marker. I specify the DRC subclass layer that it will display upon, and I can add a quick description for the next person who picks up this rule set to know what that rule is specified for. Quickly run an update, and I can see a DRC violation now with the stiffener that's interfering with the actual bend area. And I can see from the list information here what my values were and how the values were violated. Now, using shape edit mode, I simply grab the boundary of the stiffener, slide the stiffener up, and I can see interactively that the DRC marker has gone away and I've corrected the issue. Let's take a look at another rule set where I want to apply an adhesive for that stiffener to make sure that it adheres to the flux area. And I want to be certain that this adhesive is within the boundary of my stiffener so that there's enough clearance that when the stiffener is pressed into the flux design, there is no epoxy oozing from outside and causing other issues. So again, I define the spacing, the label, add a note, and now I'll add the geometry that represents the adhesive. And I can see that I've instantly created a violation where I have not met the spacing criteria for that adhesive. So I re-add the geometry, and now there's no violation. Another practical application for interlayer checks would be in a situation where I have a transition area. It's important to keep holes away from these transition areas, especially if the holes are pre-drilled, and we don't want any adhesive to flow into those holes causing interference. So I have a transition zone defined in my design, and I select a top layer as an example for my pins and vias. Again, I add the gap spacing that's required with the DRC label, and I could add this DRC on the top etch layer. I wish I don't have to do it on the interlayer check DRC marker layer, but I do see the violations that have occurred based on that rule, and now I just simply use slide to move the vias away from the transition area, which is the light green rectangle you see, and now I've cleaned up all my violations. As mentioned, one of the critical aspects of rigid flux design is passing that design stack-up intent to the manufacturer to ensure that the product is built correctly. The Allegro 17.2 stack-up tool allows you to create the cross-section definition in a table or in a graphical format. The table includes the materials that are assigned as well as the zones that reference those particular stack-up definitions. I can also represent that stack-up information graphically by having an individual stack-up definition based on my cross-section editor. So let's take a quick look at that, show how it works. At my manufacturer, I select the cross-section chart, select the table tab, add a title for that table, select my default text block sizes and the particular columns that I want to display, select create, and I simply just add the table right to my document layer. You can see all the materials, the stack up order, and the zones assigned. And I can also create the multiple stack up graphics. Select the options and the display items that I want to see in my graphics. Place those in my document layer and move them around, space them out a little bit. And here we can see the graphical representations of those stack-ups. So these tools can save time in documentation by dynamically generating those based on the stack-up information. So what have we looked at? So we've seen how Allegro supports rigid flex design through specific subclasses for rigid flex design, the process for defining multiple stack-up definitions, and the stack-up zones which reference those stack-up definitions and how important zones are when it comes to placement and routing. We've seen bend area definitions that are easy to use and define the bend area and the parameters based around those, as well as enhanced etch and shape editing capabilities that make life easier when working with these type of designs. Interlayer checkings, those critical rule checks that go between mask layers and other types of layers to verify for clearances and overlaps that are required in my design process, as well as the automated cross-section generation details for documentation. So we see how well Allegro has done in supporting rigid flex, eliminating a lot of workarounds that used to tie up so much of our time, and now it's just part of the tool. It makes life much more easier now in creating rigid flex designs. There are a couple additional resources you can reference that are available. First is the PC Design blog on cadence.com. Put up a nice little article on there on supporting multiple stack-ups for rigid flex. Also, there are some papers on the Cadence Online Support site where there's a best practice paper that I had written to help you, guide you through the process of creating a stack-up using the new technology, as well as the other features for rigid flex design. And there are other papers on there as well that address those items, and those are listed here on this slide that I'm showing.
Thank you, Ed. We're happy that the resources keep coming related to making it a clearer picture for our users about these tools. So now we have 4 next steps and a thank you from our team. Now to wrap up. Number 1, please work with your team to evaluate and upgrade to Cadence PCB Tools 17.2. This is where all the cool features are. So please, I know it's a struggle for some of your design communities to keep updated, but we believe it's worth the effort. And please reach out to your Cadence sales contact if you're having thoughts about this migration, and let us help you with that. Number 2, get trial licenses for other options that you see that are interesting. As we said today, rigid flex features are available in the base product, so you don't need licenses for this. But in general, don't forget to ask for trial licenses to try new things. And also, we'd really be happy to see you and others on your team attend future webinars live. Please use this link to view earlier webinars and register for future webinars under cadence.com company events. We have quite a few webinars in the pipeline, which will go deeper on the topics of real-time concurrent PCB design, auto-interactive routing, and high-speed interfaces. We would also like to invite you to participate in our PCB design community, where we publish blog posts on new features, tips and tricks from our support staff, and upcoming events. If you subscribe to our PCB design blog, you will get a short email when we post new content. Ed and I and the whole Cadence PCB team thank you for joining us today. We look forward to seeing you again at a future webinar or a local event. Have a great day.